Hello everybody. In this particular class we shall discuss arithmetic logic unit. Often we term it as ALU, the abbreviation of it. And arithmetic logic unit, as you understand from the very name of it, that it is one unit within which both arithmetic and logic operation are to be done. The idea is that if you are looking for a circuit which is to be used in a general purpose device, so you do not know for sure that what this circuit is going to do. So, when it required it will do some logic operation, when required it will do a different logic operation, or it might do even arithmetic operation of one kind or the other. So, would you like to have many such possible circuits and then invoke one of them when it is required and others are remaining idle at that time, or would you like to have a device which can do all the different functions, many different functions, and you have appropriate selection input by which you choose which arithmetic or logic operation you want to do. Okay. So, for such general purpose device, you would be preferring an option like having a arithmetic and logic computing unit, and which will be used by the main processor or the other processing units. Okay. So, this is the idea. So, you can understand that when you are talking about such unit, it is relatively complex in design when you look for practical use of say using it for 4-bit, 8-bit kind of thing, and many different functionalities are involved. So, what we shall start discussion on this by in step by step manner, so that we do not get frightened by looking at the bigger circuit, more complex circuit having about 70 logic gates or so. First we look at a simple circuit where we are doing a 1-bit operation, and the operation that we do here is either a logic operation NAND, okay, or NOR, or a half addition. Okay. So, this is the thing that we are doing, right, and so it has got two inputs A and B. So, these are the operands, you can say, and the result of the operation is coming out in y0 and y1, and S is the select input. Only one select input is there. So, it is selecting. If S is equal to 0, then y0 output will be a logic operation AB and NAND of AB, and at that time y1, if you look at y1, if you sample y1, you will get A NOR B. Okay. But if S is equal to 1, then what you get is the half addition. So, y0 will be the sum bit, which is XOR of A and B, right. So, A prime B plus A by AB prime, and y1 will be the carry bit. So, this is the carry bit. So, that is AB. We all know about it. So, we have seen this before, right. So, how would you write the circuit inside for this simple 1-bit unit? So, with very simple logic function and arithmetic function that we have seen. So, you will be writing S prime, okay, when this is the case for y0, S prime AB prime for here for this particular case, and S plus that is ORed with when S is equal to 1, A prime B ORed with AB prime. So, this is how we will write it. Okay. And if you do simplification, then you can see this is the way y0 will be related to S, A and B. And if you look at y1, how will you write it? So, S prime and A plus B prime, right, and S A B, this is coming from here, right. So, if you take it there. So, this you from the De Morgan's theorem, S prime, A prime, B prime, and S A B. You can see that this is the simplified version of it. So, you realize them. So, it does the operation. So, it is relatively simple. Okay. Now, let us look at a more complex thing. So, here we are having a 2-bit operands, right. So, A0, A1, okay, here, and B0, B1, and the corresponding outputs are Y0, Y1, okay. And we have additional input carry in and carry out. These are additional inputs, okay. And now we have got two select inputs, S1 and S0, okay. So, what we see here, so we look at a function table now, okay. So, for S1 and S0 0 and 0, 0, 0, so we ignore the carry in, we do not take into consideration the carry in at that time, and the output at that time is A NAND B, NAND of A B, okay. So, by this what we mean? We are meaning bitwise operation, okay, right. So, that means Y0 is A0, NAND B0, Y1 is okay, Y1 is A1 NAND B1. So, that is what we mean by this. Is it okay? So, similarly, for 0 1 we are having NOR operation, bitwise NOR operation. So, these are the thing that is happening for these cases 0 0 and 0 1, and for 1 0, if carry in is 0, y is equal to 1, and if carry is equal to 1, this is A plus 1. Now, we are introducing the term plus to differentiate it from the sum operation that we do with this symbol, okay. So, A plus 1, and when these selection inputs are 1 1, right, if carry is 0, this is A plus B, and carry is 1, this is A plus B plus 1, okay. So, that means it includes the carry in, right. So, basically what you are doing is a full adder, full addition, okay. So, this is what we are doing, is it okay? Now, how to develop the circuit for this? So, we can see, I mean basically it is a now 5 variable problem. So, S1, S0 and C in is there. So, if C in is 0, so to make it understandable here. So, if C in is 0, okay. So, at that time for these options S1, S0, 0, 0, okay. So, when A0, B0 both are 0, this is NAND. So, this is the line we are talking about. So, this is 1, right. When one of them 0, A0 is 0 and B0 is 1, NAND output means this is 1. When both of them are 1, NAND means this time it is 0. When A0 is 1 and B0 is 0, this is 1. So, this is the way you can complete this one, and this is the corresponding truth table, right. And you can have a relationship going forward for a 5 variable problem and minimize, and you can see the circuit, okay. And you can see if it is now multiple outputs are there, whether you can take some intermediate output to the next level. So, this is the way you can visualize a 2-bit arithmetic logic unit, which is doing two set of two logic operation, okay. And essentially this is one mathematical operation, arithmetic operation, this is one, just carry part is included in one case and carry is not included in the other case, okay. Basically it is not too different. So, basically with two inputs you can have 4 possibilities, 2 is assigned to arithmetic and 2 are assigned to logic, okay. Now, we go to something which is actual arithmetic logic unit IC that you might use in the lab, okay. This is IC 74181. So, you can see it is a 24-pin IC, and in this IC this is a 4-bit arithmetic logic unit, 4-bit arithmetic logic unit, and the inputs are A0 to A3, where you can see them A0 to A3, A1, A0, A1, A0, A1, A2 and A3. This is active low, right, and B0, B1, B2 and B3, right. So, these are the inputs. So, selection So, selection is designated by S, S0, S1, S2, S3. So, what it means? So, it tells us that some 2 to the power 4, 16 possible operations is possible. Okay. Actually not, you can do more than that, because you have, it has got an additional unit input called M. M stands for mode. So, if M is equal to high, it is logic operation, and M is equal to low, it is arithmetic operation. So, for each of these cases of M, you have got 16 possibilities. So, total 32 different possibilities are there, 16 arithmetic operation and 16 logic operation is possible through this particular ALU. Okay. And this is the carry input which can be taken from previous stage or another logic circuit, and this is the carry output which you can take to the next circuit. So, it can be used for replicatory addition if you so require. Okay. And other than that, you have this group carry generation and group carry propagation term that is getting generated out of this, which is useful, which could be useful, and we shall see one such framework by which these two group carry terms are used for first addition. So, internally it is doing first addition, but if it is to be connected to the next stage or other stages, if you want a replicatory, then this is there Cn plus 4, and if you want look ahead carry generation, for which you need G and P term getting generated, then they are also there. Okay. So, equality A is equal to B, this output is generated, but not A greater than B or A less than B, that I told, right. And then these are the main outputs for this operation A and B, where A and B are operand, okay, are generated from F0, generated at F1, F0, F1, F2 and F3. Is it clear? Right. So, when you look at the function table, we shall see the arithmetic operations that are being done include addition, subtraction, okay, shift of operand A. So, A is considered as the main operand here by one position, right. So, then magnitude comparison not directly, because there is, you see there is no direct output as A greater than B or A less than B. A equal to B is there, but not the other cases. So, by some other means we can do it, and we shall see that logic operation like NOT, AND, OR, NOR, XOR, XOR, all these common things are there, and more than that also it is there. Okay. So, this we shall see. So, this is the function table. Okay. So, again it might look little bit heavy, but because there are 32 different possibilities are there. So, this is M is equal to H, right, the logic function it is generating. Okay. So, this these are the different logic function for choices of S3 to S0, say L, 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 that means all of them are low. So, at that time whatever at these function outputs F3 to F0 will be the complement of A3, A2, A1 and A0. So, that is what it says, that is what you will get, right. That is the way the circuit is developed. We shall look at one example also after a few slides. Is it okay? So, next one is similar, the different logic functions. You can see the one that I told, that NOR will be available, okay. XNOR is there. So, many other things are there. We shall see what are they and what is its implication. And similarly, for logic M is equal to low. So, depending on presence of carry and absence of carry and presence of carry, the meaning is different. If in one case, if it is A minus 1, when carry is included, it is F is equal to A. Okay. So, it just input is passing through to the output. Okay. So, the different classes, okay, A plus B and then A plus B plus 1, right. So, these are so A minus B and this is A minus B minus 1, right. So, these are the different functions that you can get and make use of. Okay. Now, one thing important here, the A is equal to B, the magnitude comparison output, okay, the magnitude comparator output here is open collector. Okay. So, open collector we understand what does it mean. Basically you need a additional resistance, and it is connected to the power supply through which actually the circuit operates. Other than that, what we know, and it can deliver more current. So, other than that we know that it can offer wired AND connection also. So, if you have another say a 4-bit comparison being done by another say ALU, which also has got open collector output for A is equal to B. So, those 4 bits and these 4 bits, if we just add make a wired connection, I mean just connect the wires there. So, it will be giving an AND logic. So, if both of them are high, right, then you can say as a whole this 8-bit number is high, I mean as a whole 8-bit number is equal. If one of them is low, then of course equality is not established. So, something else is happening, right. So, this is giving you a very quick comparison between two numbers which are being compared in two different ALUs, okay, by making use of the wired AND option of a open collector output. Okay. So, there is no multiplication as such, but A plus A means 2 into A, which is basically a left shift of 1 unit of A. Okay. So, that is what you can see, and for magnitude comparison, okay, there is no such it's a separate input. So, you can look at the result, okay, this carry getting generated. So, we have noted what is the implication of the carry, right. When you are doing the subtraction, okay. So, L H H L. So, what is it? So, this is the one, okay. So, in one case it is A minus B minus 1, another is A minus B. So, in the last class for magnitude comparison, we have seen that how to get it done through subtraction, right, and so we told at that time that ALU will be using subtraction for that. So, if it is low and this is low, right, then we can tell that this is A less than B, okay, less than equal to B. It is low, it is high, it is A greater than B. You can see the 2 complement arithmetic how it is done. This is high and this is low, then it is A less than B, and if it is high, it is high, then it is A greater than B, by which you can get the magnitude comparison done, okay, by understanding these carry output Cn plus 4, okay, in presence of or absence of Cn, okay. Now, the function table, as I said, we had these logic functions, right. So, if you look at closely the logic functions that are there, you will see that the outputs here connects to this table on a one-to-one basis, okay. So, what is that and what is this table? So, this table we had seen in one of the earlier weeks of this particular course. So, with 2 inputs, what are the many different functions that are possible, okay. So, we found that 16 possible functions could be there with these 2 inputs 0 0 0 1 1 0 1 1, okay. One possibility is that for each of these cases the output is 0. One possibility is that only for 0 0 the output is 1 and the rest of the cases it is 0. One possibility is that for 0 1 it is 1, rest of the cases is 0. So, with this 4 you can have again 2 to the power 4, 16 different combinations of zeros and ones, okay, generating 16 different functions, right. We had seen where we had got AND, OR and those kind of cases, okay. So, if now for each of these cases LL, the first one we designate it by number 1, second one we designate by number 2, this is number 1, this is 2, this is 3 and so on and so forth. You can identify that in this particular function table, right, 1 is somewhere. So, here is your 1, okay, which is not there in other places because each one of them is unique, okay. So, LL for this thing, this is A bar, and you can see this is 0 0, this is 1, and this is 1, this is 0 0. So, this is A bar. Similarly, you can find out 2 appearing here, 3 appearing here, and that way each of these functions, possible functions, are actually covered by this logic operation. So, if you need any one of them, okay, you can make use of them if so required by invoking appropriate selection inputs, Is it clear? Now, this is the IC 74181 circuit. If you look at the manufacturer's data sheet and all, how it is there. So, as I said, it is a bit complex. So, that is why we began with a simpler version of it. Okay, but now we are in a position to understand what it represents and how it works also. Okay, and we can look at one example case. We look at one example case where the selection input is all 0, right? M is equal to 1. M is equal to 1 means it is a logic function, and B is all zeros, right? Cn is also 0. So, if this is the case 0 0 0 0, then what we are expecting, f is equal to a prime. This is beta is an complement operation, right? So, we expect that f naught will be a naught f naught a naught bar, right? So, that means when a naught is equal to 0, f naught will be 1, a naught is equal to 1, f naught will be 0. So, this is what we expect. Similarly, for other cases, right? So, and it does not depend on B, and Cn is immaterial. So, that is what we expect, and we can see whether it is happening or not. Let us look at one such example case. So, this is where a naught is given. So, we have considered the case a naught given as 1 in the blue, okay, and a naught given as 0 in the brown. Okay, you can see the colors, right. So, when so I am trying to make it cleaner. So, this a naught is 1, okay. Then what is happening? This is 1 is coming over here. For NOR gate, 1 is there means this is 0, the output is 0, okay. And the other inputs, this AND gates, you can see it is coming from selection, all selections are 0. So, these are 0 0. So, this is also 0 0 because one of the input is connected as the selection input, which is 0 0, right. So, 0 0 this NOR gate, this output is 1, okay. Now, we look at the other cases. So, this is this XOR gate 0 and 1, this is the input. So, this is this output is 1. So, for the final output for F naught, this is the XOR gate which is giving input 1, okay, and you have to look at this NAND gate output. So, this NAND gate output, it has got m is equal to 1 here because it is a logic operation. So, the NOT gate output is 0. So, 0 to an AND gate output means it is 1, okay. So, 1 1 for an XOR gate, we know the output is 0, okay. This is clear. So, for A naught is equal to 1, F naught is equal to 0. Now, if A naught is made 0, so this is made 0, what is changing, what is different here? So, A naught is 0 means this is becoming 0. So, this NOR gate output, now all the inputs are 0. So, this output will now become 1. This NOR gate output is already 1 because of these selection lines are 0, right. So, this is 1 1 means this is becoming 0, right. So, this XOR gate, one of the input is 0 and the other input is 1 because of the m being 1. So, NAND gate is output is 1, okay. So, 1 and 0, then this output is 1, is it fine? So, you can see that this is happening. So, you can see for other cases also, and it works in that manner. Just Now, what we look at other than this the way the function table it works and all, how ALU can be work in tandem with look ahead carry generator. So, IC 74181 and IC 74182. Okay. So, look ahead carry generator is 182, which we had seen before, right, when we discussed first adder. So, here we show you a framework which is available in the manufacturer's data sheet. If you go to the TI's Texas Instruments website and all, you can figure it out. So, where you can see that the addition where we are using 64-bit addition. So, for this 64-bit addition we are using basically 64-bit operation we are doing, okay, using 16 ALU, each is 4-bit, right, each is 4-bit long. So, 74181, so you can see the first level 1, 2, 3, 4, 5, this way 16 such cases, 16 such units will be there, okay. And the G and P term we had seen in the ALU, these are the terms that are there. So, 4 of them can go to one IC 74182, right, and this IC 74182 is generating Cn plus x, Cn plus y, this carries in so that is getting connected here for each one of in the generation process, right. So, this we have seen in the previous case how 782 works, 182 works, right. So, similarly for this one, so 4 such look ahead carry generator will be there, okay. So, they are again generating this group carry generation and propagation term out of them, because the circuit is similar, right, and then this will be again fed to next level of IC 74182, which has got which can take 4 inputs, okay, and then you can get the final carry out of it. So, basically this is the way you can use 74181 and 74182, and using multiple levels you can get the carry ahead of normal ripple carry based addition would have given, okay. And we have already noted that the 74181 also generates the normal carry which can be used for Cn plus 4, which can be used for ripple carry addition if it is so required, okay. So, to conclude, we find that ALU is a versatile unit that can perform arithmetic and logic operation on operands according to control inputs, which is coming through those selection lines. It is a 4-bit ALU IC 74181 with the mode select input, and depending on whether it is high or low, logic or arithmetic operations are done, and it includes commonly used NOT and these operations, and in fact it can generate all possible combinations of 2 variables, that is 16 possible functions. And arithmetic operation includes addition, subtraction and magnitude comparison by indirect manner, and then it has got additional inputs like ripple carry, group carry generation, propagation term, equality, and IC 74181 can be connected to IC 74182. A combination can be prepared by which look ahead carry for more than 4-bit arithmetic is possible, okay. Thank you.